Okay, welcome to section 7 in chapter 10. We're talking about the properties of logarithms. These are the rules that allow us to do arithmetic with logarithms. So the first question and our first goal is, what are these properties? What are these rules? So that's the first thing we're going to talk about. We're then going to talk about how one of the most important rules, the rule that we'll use when we start to do algebra with logarithms, is derived. We're then going to talk about how to evaluate logarithms using a calculator so we can get a numeric value for our logarithms. And then, with all of that, we'll be able to do some algebra. We're going to solve logarithmic equations. So, a lot on our plate. Let's get started. So, first off, the product rule. So the product rule says that if you've got a product inside the argument, that comes out and actually gives you two separate logs, the sum of two logs. So the fancy way of saying this is that the log of the product is the sum of the logs. Now notice that that's definitely a rule. It goes both ways. We can make the left side into the right side or the right side into the left side. But there's a lot of logarithmic expressions that we can write that we do not have a rule to simplify. The log of the sum, the product of the logs, or if the bases are different. Now take a look at what we get on the right side here when we use our product rule. The bases are the same. Now that's assuming we're going from the left to the right, but we can go from the right to the left. We can actually take the sum of logs and rewrite that as a product. But that's just a reminder. That last example of things that we can't do is a reminder that if the bases are different, we can't use our rule. So our first example here is the log base 8 of 8, and of course that's equal to 1. The reason that that's equal to 1 is because the exponent on 8, remember a log is an exponent, the base is 8, and the question is, what is that equal to? Well, it's equal to 8. So 8 to the first power is 8. The log base 8 of 8 is 1. Here in our next example, we've got a sum. We're adding two logarithms, and notice that their bases are the same. So we're basically working in the opposite order from right to left. And we're going to use our product rule to make this sum into a product. So we'll take that multiplication inside, and that'll give us the log base 8 of 30. This next example, the 24, we can rewrite that as a product. In fact, we can rewrite it as 4 times 6. Notice that I chose the factor of 4 because it matches the base. Then we've got the left side of our product rule. We're going to make that into the sum of logs. So that will give us two logs, the log base 4 of 4 plus the log base 4 of 6. And just like our first example, the log base 4 of 4 will give us 1. So this is 1 plus the log base 4 of 6. Matching the product rule is the quotient rule. It makes the quotient into the difference. Now notice that that is perfectly analogous to the product rule. The product rule makes the product into the sum. The quotient rule makes the quotient into the difference. And again, notice that there are no rules to simplify a log of a difference or a difference of logs if the bases are different. So if we're going to go from right to left in our rule, we have to check that the bases are the same. So our first example is the log base 7 of 7/9. That's the log of a quotient. So we can start with the right side of our rule and rewrite that as the difference of the logs. So the first thing we're going to do is rewrite that as a difference of logs. Notice that the log base 7 of 7 is 1, and so we can simplify this as 1 minus the log base 7 of 9. Our next example is going from the right to the left side of our quotient rule. We can do that because the bases are the same. Those two 3's give us 2 of the same bases. So we're going to go from right to left. We're going to make this difference into a quotient inside the logarithm. Now take a look at that numerator, x squared minus 9 factors. It's factors as x plus 3, x minus 3, and of course the x plus 3's cancel. That leaves us with the log base 3 of x minus 3 with the reminder that x cannot be negative 3. And that's certainly because we cannot divide by 0. So that x plus 3 in the denominator is 0 when x is negative 3. So we can't have that. So x cannot be negative 3. Our next example, the log base 4 of 3/16. We're going from left to right. We're going to make the quotient inside the log into a difference outside the log. So we rewrite it using the rule. Now we notice that 16 is 4 squared. So we rewrite it in that way. And we see that the log base 4 of 4 squared, well, the log is the exponent. The base is 4. So the log base 4 of 4 squared must be 2. So the next thing that we're going to do is we're going to look at how this rule is derived. So we're going to ask the question, how did we make the power rule? So the power rule says that that exponent comes outside. It becomes a coefficient. So let's take a look at using our product rule to make the power rule. So here is the log of x times x times x times x m times. So that's the same as multiplying x times itself, m times, that's x to the mth power. But notice that for each of the factors of x, we can use our product rule to bring out a log of x. And we can do that m times. And if we've got m terms, remember terms are being added, we can say that that's the same as m times the log base b of x. So there's our power rule. Our power rule will allow us to do algebra when the time comes. So it's very useful to us. In fact, it'll allow us to do something algebraic with logs. This is foreshadowing something that happens in a coming section. But I'm just pointing out now that the power rule is what allows us to take the log of both sides. That is, not only are we going to be doing algebra with logs, that is, solving logarithmic and exponential equations, but we're actually going to use logs in the way that we use multiplication and division and all of our operations as an inverse operation. So when we see an exponential, we'll be tempted to take logs. So here's our power rule. Our power rule says that if you've got an exponent of the argument of the log, that can come out front as a coefficient. Of course, our base has to be positive and not 1, and x has to be positive. So we're reminding you of that from earlier. So let's take a look at using the power rule on a numeric example. So here's the log base 3 of 25. So that 25 factors as 5 times 5. Well, 5 times 5 is 5 squared. And so we're doing exactly the power rule. We've got a log with an exponent. So here the exponent is 2. That's taking the place of m in our rule. So we can bring that 2 out front. And when we do that, we've got 2 times the log base 3 of 5. Our next example is even more straightforward. The exponent is clearly 4, so no factoring there. It tells us exactly what it is. So that 4 comes out front and gives us 4 times log base 3 of x. So we've used the power rule to make an exponent into a coefficient. Our next example already has a coefficient. So now we're seeing, convincing ourselves that any rule in mathematics can be used 2 ways. We've been using it from left to right. We're now going to use it from right to left. That 5 out front is about to become an exponent. So when that happens, we're going to have y to the 5th power. And similarly, in our last example on this page, that 2 out front, that coefficient of 2, is going to become an exponent on x minus 3. So it had to happen. Here are some more interesting exponents. In this first case, we've got the cube root of y squared. So we're going to use what we know about fractional exponents and make that cube root into the denominator of the exponent. So notice how that 3 became a 1/3. And notice too that the multiplication inside of the logarithm, that is x to the 14th times y to the 2/3, came outside as addition. Now once we've done that, we can use our power rule, and that power rule says that the 14 becomes the coefficient of the first logarithm and the 2/3 becomes the coefficient of the second logarithm. We can also do this with more than 2 factors, with more than 2 things that we're multiplying and dividing. So here the x to the 16th and the y to the 10th are being added because they're in the numerator, they're being multiplied, and the z to the 4th, when it comes out of that logarithm, it will be subtracted. So let's take a look at that. There's the addition for the things that are in the numerator. Now another way of thinking of this is, instead of saying, well, we're adding the log of y to the 10th, is to say that that term is positive. And it's positive because we're multiplying it. Now notice that the other positive term here is the log of x to the 16th. And it's positive for exactly the same reason. It's positive because we were multiplying it. The only negative term is the factor that came from the denominator, the z to the 7th. And if there had been more factors in the denominator, they would have simply come out with negative terms. Now we can use our power rule that says that these fine exponents are going to come out front. So for example, that x to the 16th is going to give us a coefficient of 16. The y to the 10th will give us a coefficient of 10, and the z to the 7th will give us a coefficient of 7. Now, what role do logarithms play? Now this is how we lead up to doing algebra with logarithms. And we do that by reminding you that the log is the inverse of the exponential. They're the inverses of each other. So b to the x and the log base b, what one does, the other undoes. Now remember how this looks in function notation. It basically says that the function and its inverse undo each other. So if you look at where this statement starts and you look at where it ends, you can remind yourself of the generic properties of inverse functions. So looking at the left side, the inverse function of f of x is, jumping all the way to the right, x. In other words, whatever f did to x, f inverse undid that. So we're basically showing that these two functions, b to the x and the log base b, are in fact inverse functions, that what one does, the other undoes. And we've seen that, you've seen that since your first look at algebra. Multiplication undoes division, subtraction undoes addition, the square root undoes the square, the cube undoes the cube root, and so on and so forth. So we're now showing that these two functions, the exponential and the log, are in fact inverses. So let's go through and do this. So the first part of this, we're working inside. We can think of an inside of a function. F of x is b to the x. F inverse is the log base b. Now, that is exactly what you'd expect. The log undoes the exponential, and we've got that x out. Notice that we could do this in the other order. We could say f of f inverse of x, in which case we'd say f of the log base b of x. And as odd as it looks, that's b to the, that is raised to the power, log base b of x. The exponential and the log undo each other. Now, you can think of this verbally too. You can think of this expression, the log base b of x. Well, first off, that's the log base b. And the log base b is the exponent if b is the base. It says, tell me the exponent if b is the base. But then look at what we've got. We've got b of x. Well, b of x has b as the base and x is the exponent. So this is asking and answering its own question. The log base b asks the question, what's the exponent if b is the base? And the second part says that b is the base and x is the exponent. So taken together, that asks and answers its own question, and we're left with x. So, written without so much space in there to fit the English sentences in, we can see that b raised to the log base b power of x is x. So, if b is the base and the exponent is the exponent with base b, so that it equals x. Exactly what it says. Anytime you learn a new operation, it's nice to know the arithmetic on it. One of the things that we did without mentioning it too much is we talked about the fact that a log doesn't have to show its base sometimes. And that's true when the base is 10. So the log base 10 is simply defined to be the log. You can show that 10, and if you're doing algebra, sometimes you have to. Similarly, the log base e, and we've seen e and actually learned where e came from in the section where we derived the formulas for compound interest and continuous growth. The log base e is ln. That's the logarithm base e. It's read ln, and it's called the natural log. Now, to actually use our calculator with all these bases running around, we need the change of base rule. So basically what the change of base rule allows you to do is it allows you to evaluate a logarithm with any base. If you look at your calculator, you don't have a log base b key. It might be hidden in a menu somewhere, but it's not on the keyboard itself. What you've got on the keypad is the log and the ln. So using either of those two keys, you can calculate the log base b of x. So any base and any argument. So using change of base, let's evaluate, that is, find a calculator approximation for the log base 3 of 17. So first off, we're going to use our change of base rule. We're going to make this into expressions that our calculator can actually perform. This is the log of 17 over the log of 3. Notice that whether you've got a scientific calculator or a graphing calculator, you're going to have to press the log key twice. There's no shortcut around this. And that's true because there's no rule for the quotient of logs. So when you've got a quotient of logs, you've got to evaluate both those logs separately. And when you do that, you get, and I rounded this to 4 decimal places, 2.5789. Now let's take that 2.5789 and let's make it the exponent on 3. What we're doing here is checking. Notice that this is the inverse operation. We're seeing if this really is the exponent that when you put it on 3 gives you 17. Now when you do this in your calculator, you're not going to get 17 exactly because we rounded this fairly dramatically. But you're going to get something really close to 17, which itself rounds to 17. So this, in fact, is an excellent way of checking that you've done a logarithm correctly. Because remember, you've had to use your calculator, you've had to use the change of base rule. And it's relatively easy. You've got this number in your calculator, you can say 3 to that answer, press enter, and you'll get something really close. Okay, another example. Remember that the log is not division. If we were doing division, we'd do division. The log base 7 of 14 is certainly not 2, because remember 7 squared is 49, and a log is an exponent. It says what exponent on 7 gives me 14? Clearly not 2. 2 would give us 49. So we're going to do this in our calculator. We're going to use change of base, and out pops 1.3562. One of the things that I like to do in the workbook is give my students steps for solving problems. So here's 4 steps to solve logarithmic equations. The first is to rewrite without coefficients, that is to get rid of coefficients. So if you've got a coefficient there, use the power rule to make it into an exponent. Now we need to do that because our next step is to use the product rule and the quotient rule. And recall that the product rule and the quotient rule don't have coefficients. It's either a positive or a negative. If it's a positive, we're using the product rule and we're multiplying. If it's a negative, then we're downstairs to the denominator. So that first step gets rid of coefficients. Then the second step makes several logarithms into one logarithm. Remember that if you are adding logarithms, those become factors in the numerator, and if you're subtracting, those become factors in the denominator. And then translate. So we've been doing that. We've been using the definition to rewrite a logarithm as an exponential. Now, after you've done that, you can solve it. And the last step is to make sure that our solutions actually work. And the reason that that is an issue is because the argument of a logarithm has to be positive. And that's true because that's the only way that we can have a real valued logarithm. Now, that isn't to say that we can't have negatives as arguments for logarithms, but that makes the logarithm complex, and we want to avoid that. So we require that m, our argument, is positive. Okay, so we're going to solve this logarithmic equation. Notice that to begin with, there's a coefficient, so our first step is to use the power rule to make that into an exponent. Then notice that we are subtracting, so we're going to have a quotient. Now that works because our two bases are the same. They're both 2's. So we can rewrite this as a single logarithm, and that logarithm is a quotient. In other words, the positive logarithm gave us factors in the numerator, and the negative logarithm gave us factors in the denominator. So that's step 1 and 2. Now we translate. We read this correctly, and that means that we say the log base 2, so we know what the base is, and then we say that the log is the exponent. So that tells us that our base is 2 and our exponent is 1. And that's equal to the argument, x squared over x plus 4. We solve this. I would simply cross multiply, so that 2 gets multiplied by x plus 4, and that's equal to x squared. We see that this is quadratic because of the squared term, so I'm going to try the zero factor property. So that means getting everything on the same side of the equal sign so that it's equal to 0. So there's the 0 in the zero factor property. And then we factor. We say one sum product, and that gives us our two solutions. So we see that x could be equal to 4, or x could be equal to 2. Now both of them are positive, so we can take their log, that is, and get a real number. So the solutions are 4 and 2. Okay, so here we are working through several of these examples. In this first example, notice that there are no coefficients, so we don't need to worry about step 1. And notice that the bases are the same, so we're all set for step 2. So we're going to use the product rule that gives us the product of those two arguments. We're then going to translate. The base is 3, the exponent is 1, and that gives us 3 to the first power equals that argument x squared plus 2x. This is quadratic, so we're going to try the zero factor property. There's the 0, and then we factor. This gives us two solutions, x equals -3 or x equals 1. Now when I plug in the 1, I'm taking the log of a positive number. But when I plug in the -3, I'm taking the log of a negative number. And that'll give me a complex answer, and we want to avoid those. So we're going to throw out that solution and say that x is -1. In the next example, we notice again that there are no coefficients and that the bases are the same. So we can use the quotient rule here. We say that that difference is going to give us a quotient, the result of performing division. Notice that that numerator is a difference of squares, so we factor it, x plus 2, x minus 2, and of course the x plus 2's cancel. And now we're in the situation where we can translate. So we say this correctly. We say the log base 5 and that the log is equal to the exponent 1. The base is 5, the exponent is 1. So 5 to the first power equals x minus 2. Well, let's get the x by itself by adding 2 to both sides, and that gives us x equals 7. 7 is positive, and it looks like when we plug it in, we get positive arguments because we're squaring and subtracting 4. So let's take a look at that. That subtraction is a little bit of a concern. So I'm going to see what happens when we plug in x equals 7. Well, the first thing is we square it. That gives us 49. And then we subtract 4. Well, 45 is positive, so it looks like that works out fine. So x equals 7 is our solution. Okay, some more of these logarithmic equations. Looks like there are no coefficients and the bases are the same. So we're going to see that we have subtraction. That subtraction is going to give us a quotient. So we'll translate the difference of logs into the log of the quotient. And then we can translate this. If we say it correctly, we say the log base 3 is equal to the exponent negative 2. So the base is 3 and the exponent is negative 2. So we translate this. 3 to the negative second power equals that argument, 2x over 3x plus 15. That negative exponent tells me that the base is in the wrong place. That tells me that this is something that instead of being in the numerator wants to be in the denominator. So that becomes 1 over 3 squared. I'm going to multiply across. Of course, 3 squared gives us 9, and we cross multiply. When we multiply a numerator by the other denominator. So we multiply 9 by 2x, and we multiply 1 by 3x plus 15. This is a linear equation, but we still need to simplify that right side. 9 times 2x is 18x. And then we get rid of the 3x by subtracting 3x from both sides. And then we get rid of the coefficient 15 by dividing both sides by 15. And 1 certainly works. 2 times 1 is positive. 3 times 1 is 3, plus 15 is 18, and that's positive. So we're doing that fourth step, checking. The next one, very similar. No coefficients, and the bases are the same. We're adding, so we're going to use the product rule. That tells us that we are going to have the product of x and x plus 2. So when we distribute, that gives us x squared plus 2x. We're now in a position to translate this. The base is 2 and the exponent is 3. So we say log base 2 gives us that base of 2 and the exponent of 3. 2 cubed is 8. And we subtract 8 from both sides because we notice that this is a quadratic equation. So we're trying to solve it using the zero factor property. So we've got it equal to 0, all set to use the zero factor property. One sum product. Looks like we've got 2 solutions. And now we have a little bit of an issue. Because if I take x equals negative 4 and plug it into the argument of either of these logarithms, I get a negative. The log base 2 of negative 4, or even in the other case, negative 4 plus 2 is still negative 2. So I have to throw out that x equals negative 4, and I'm left with just the solution x equals positive 2. Okay, one more, a little bit more exciting this time, so let's see how this goes. So this example does have a coefficient. There's that 2 on the first logarithm. So we're going to have to do that first step here, which means that we're going to have to make the coefficient into an exponent. So notice how the 2 that was a coefficient became an exponent on the argument. The other thing that I did in this same step is I factored the argument of the second logarithm. So that's where we are. We've got the coefficient gone. That's the first step done. Then we noticed, we do have to check this every time, that those bases are the same. So we can actually use the quotient rule. That'll tell us that the difference of the logs becomes the logs of the quotient. And you can see why factoring was a good idea. We've got 2 factors, one upstairs and one downstairs, of the x minus 3. So they're going to cancel. And we'll be left with, and still inside the logarithm, x minus 3 over x plus 5. Now we're in a position to translate. We say log base 4 equals the exponent of negative 1/2, and that gives us our base, and our exponent. So let's simplify that. The negative exponent tells us that the 4 would be happier in the denominator, so we bring it downstairs. And then a half as an exponent is the same as a square root. The square root of 4 is 2. So we are now in a position to cross multiply. So we multiply the 1 by the x plus 5. We multiply the 2 by the x minus 3. That means some distribution has to happen. And then we're going to clean this up by subtracting 2x from both sides. That gets rid of the 2x on the right. And now we've got the opposite of x equals negative 11. We can change those signs and we get 11. Notice that 11 works. It's big enough to make that x minus 3 positive. So we needed something bigger than or equal to or bigger than 3 because we needed to make that argument positive. And 11 certainly works. 11 minus 3 gives us 8. So we've got our answer x equals 11. Now sometimes everything in a problem has a logarithm attached to it. And that gives us a different feel to our equations. It gives us a different process for solving them. Now, just like we can equate exponents, and that was the first method that we learned when we were talking about solving exponential equations, we can do the same thing with the arguments of logarithms. So here in this example, we're using natural logs, but it works for any log of any base. And that is that if you've got a log equal to a log with the same bases, then you can equate the arguments. So when you look at these first two examples, notice that everything here is a part of a logarithm. And maybe the only exception to that is this coefficient of 2. So clearly we've got to deal with that 2 first, so we definitely are, so that we've got a logarithm equal to a logarithm. And we know exactly how to do that. That 2 is going to become an exponent using the power rule. And there it is. We've now got a log equal to a log. If anyone asks you, the base of these two logarithms is 10. They have the same bases, so we can equate the arguments. That is the stuff inside. So x plus 5 equals x plus 3 quantity squared. Well, this is going to become quadratic awfully fast. We expand the right side. X plus 3 quantity squared gives us x squared plus 6x plus 9. Because it's quadratic, we're going to try for the zero factor property. We subtract an x and subtract a 5. And then we factor. So I'm thinking one sum product. So to make this work, we then use the zero factor property. And we see that negative 4 does not work. Notice that I'm only showing one of the solutions. And that's the only solution that gives us a real valued logarithm. Negative 4 doesn't work because of the second logarithm. Negative 4 plus 3 is still negative. So we had to throw out the negative 4. But notice that negative 1 is fine. Negative 1 plus 3 is positive 2. And similarly, negative 1 plus 5 is positive 4. So we've got two positives there. In other words, everything's positive and works out good for us. But we did have to throw out the solution that came from x plus 4. Okay, our next example, no coefficients, but we don't have a logarithm equal to a logarithm. On the left side, we have a sum of logarithms. They have the same base, and they have no coefficient, so we can use the product rule. The product rule says that the arguments get multiplied together, and so when we multiply x times x plus 7, we're going to distribute. That'll give us x squared plus 7x. And of course, we can equate the arguments, which means those natural logs go away. Another quadratic equation, going to get 0 again, going to factor, and then going to look at those solutions. Now, that second factor gives me a solution of x equals 2, and that certainly looks good to me. When I plug 2 into the first log, I get the log of 2. When I plug it into the second, I get the log of 9. So 2 certainly works. But I'm worried about this first factor. It gives me a proposed solution of x equals negative 9, and that's a problem because that makes both of the logarithms with a variable in them negative. Negative 9 and negative 2, so we're only going to have one solution here, and that is x equals 2. Okay, two more of these. Logarithms all over the place. Everything's got a logarithm in it, so we're going to equate logarithms eventually. But before we get there, we're going to notice that we're adding and subtracting logarithms on that left side. Now, anything that's positive, the positive logs are going to give us factors in the numerator. The negative logs are going to give us factors in the denominator. So we're going to multiply the x times the x plus 3 upstairs, and we're going to have the x plus 13 downstairs. That gives us a log equal to a log, so we can equate the arguments. That is the stuff inside. You can just think of getting rid of the logs. That's true because logs are 1-to-1. Now, I'm going to cross multiply. I'm going to expand in the numerator, that is, distribute that x, and we get something that's definitely quadratic and heading towards the zero factor property. So we'll subtract 8x, we'll subtract 104, and this factors kind of nicely. X plus 8 and x minus 13. Now the 13's fine because it's positive and we're only adding inside of logarithms, but the negative 8 isn't gonna work. So when you see this first factor and you think, well, okay, when I use the property x plus 8 equals 0 and x equals negative 8, I can't put a negative 8 into, well, even this first logarithm. I'd be taking the natural log of negative 8. You can always use your calculator to remind you that it will not give you a real valued answer just by asking it, what is the natural log of negative 8? So for those reasons, we only have one solution that gives us a real answer. The last example on this page, no coefficients. So we don't need the power rule. The bases are all 8, so we'll be able to equate the arguments. But we do have two logs on the left side, so we've got a little work to do cleaning those up. In particular, since we're adding that both of those logs are positive, we're going to multiply them inside the argument. So there's the 3 times the 2x plus 5. The log base 8s are going to go away, and we'll distribute. 3 times 2x is 6x, 3 times 5 is 15. This works out to a nice linear equation. Divide both sides by 6, and you get x equals 3, which works out perfectly.